Because you saw that from our previous discussions, from the assignments as well, that the schemes that we have considered so far are generally unsatisfactory, right? Either they generally either you have something like the central difference in space with forward difference in time that is completely useless because it's unstable, and then the other option was our scheme, for example, a first order upwind, which we could make stable with the right choice of parameters, but introduces a lot of numerical diffusion, and so the errors could be unacceptable. And so really all of this, like I was saying in our beginning discussion, we've learned a lot of techniques which were very useful for us to get a feel for things and get this sense of achievement about being able to do a problem with Navier-Stokes, but they're not really practical methods. Okay, first order methods in general are going to introduce too much error, and of course the ones that blow up are completely useless, even for toy problems. So we're going to look at a few other ones that have been introduced over the years, particularly in the context of fluids problems. One is called the Leapfrog scheme, and we briefly mentioned it before, a couple of classes ago. So let's look at it again. In the Leapfrog scheme, basically both space and time are discretized by a second order formula. Second order central difference formulas. So we would write then for our time derivative in the convection equation, we would consider un plus 1 and un minus 1 divided by 2 delta x. So this is our, delta t. This is our second order central difference for the time derivative plus c divided by 2 delta x, and our usual central difference here, ni plus 1 and uni minus 1 equal to 0. Or, of course, we would want to write it in a way that we can use for a time marching calculation, and we would solve for un plus 1 I, and this is going to be equal to un minus 1 I plus, remember we used the letter sigma to indicate our CFL number, so C delta t divided by delta x. So we use this sigma parameter now, our CFL number, I plus 1 and uni minus 1. Here we are then for our time marching discretization.
Should it be a minus sigma?
I've got a mistake there. Okay, yep, I put everything on the other side. Thank you very much for catching that. Okay, so let's consider now the stencil of this numerical scheme as we've done before. And let me again do this little representation of the mesh around point ni. So this would be n minus 1. This would be n and n plus 1. And this would be point I minus 1, and I plus 1. And notice now that we're getting the solution at un plus 1. So we're getting, so this is time, and this is our one-dimensional domain, and we're getting the solution here, in this point, right? ui n plus 1 here, by using the solution, the points on both sides at n, right? I plus 1, I minus 1 at n. These are the 2 points, mesh points here. And at un minus 1, we use the point at I. So basically, we're transmitting the information, if you will, in our time marching calculation in this way. So the new solution here, the new solution at this is our new solution. Depends on the value at point I at 2 time steps before, and then the value at the previous time step on both sides, on both sides, right? So this is why it's called the leapfrogging. You can see a little bit on this chart where the name comes from. Okay, so basically, UIN does not contribute. Okay. Now notice that we have 3 time levels in the discretized equation. So basically, to start the calculation, if we just have an initial condition, what do? Anybody have an idea? What would you do?
Say T.
Make something up. Okay, you want to make it up? Okay, well, it's a little bit fuzzy there. If you have 2, there's no problem, right? You can start it. But if you don't have 2 and you only have 1.
If your boundary condition was 0 at the time 0, then you would say boundary condition 0 also at time minus 1.
You could try that. Normally, what people do is, for the first time step, use another method that doesn't require it. Use an upwind, or use something that requires only 2 levels to get your first time level. And now you've got 2. And now you can start using leapfrogging from then onwards. And it's a little less fishy than just making it up, right? And just making it. So you require a starting scheme normally. You could choose which one you use for that first time step, but you require a starting scheme. Okay? So let's look at the von Neumann analysis rather quickly. I'm not going to do the whole derivation, but I just want to establish what the stability requirements of this scheme are. And, well, if you put back, remember how we did that? We put that the Fourier mode into our equation, in this case, and then you divide over by the common term, which is e to the I phi, and you divide over all over, right? And I'm going to divide over already for that term. I'm going to skip that step and just write Vn plus 1 equals Vn minus 1. You will see this makes perfect sense if you recall how we did it last couple of classes. Vn here, right, and capital I here, I'm using capital I for the imaginary number because we use lowercase I for our indices, and so it could be confusing. And so here is our expression after plugging in the Fourier modes in the equation. And so we can now write our amplification factor. We've got Vn minus 1 here, so, but the amplification factor G, which is equal to Vn plus 1 divided by Vn, is not dependent on n, so this amplification factor should be equal to Vn over Vn minus 1. For 2 consecutive time steps, the amplification factor should be the same. And so now we can divide over this whole equation by Vn, and you see here I get G, and here I get 1 over G, and the V and the Vn goes away here, and so basically we get something like G minus 1 over G equals to, this is a minus sign, right?
Yeah.
Yay, that's why. This is a minus sign, and here's my minus sign. Now it all makes sense? I got all my signs correct? Looks like. Okay, here's our amplification pattern. So we get a quadratic equation, basically I can multiply over by G, and this is a quadratic equation for G. Okay, I hope you remember your quadratic equation. I'm not going to write it all out, but the solution is G equals to I, our imaginary number, sigma sine theta. We have to use our definitions of sine with respect to the exponentials, related to the exponentials, and plus or minus square root of 1 minus sigma squared sine squared of phi. Basically, what's inside this parenthesis here is 2i sine theta, 2i sine phi, and when I take the square root of that, I get well, I'm going to get the sigma squared, the sine square, and there's also the square of I, which is minus 1, hence the minus sign in here. Okay? That's where it goes. That's how it goes. So, you see that if sigma was greater than 1, then the scheme is unstable. Since the term under the square root can become negative, and thus, if the sign under the square root becomes negative, then we have a pure imaginary G. All of these two terms are going to be imaginary, and the magnitude, when we add those two imaginary components, is going to be greater than 1. So let's see. It's best, you can see it if phi was equal to pi half, for example. So the square root term can be negative, thus G pure imaginary, and magnitude of G greater than 1. Okay, for example, if you put phi equals to pi half, you see that situation. These two components here would be both imaginary components, and when you take the norm, it's greater than 1. Now, if sigma was smaller than 1, smaller or equal, then the term in the square root is always real. And we can calculate the norm G times conjugate of G, which is the real part of G squared plus the imaginary part of G squared, and that's going to give us 1 minus sigma squared sine squared, and plus sigma squared sine squared again, which is identically equal to 1, which means that the scheme is neutrally stable for the convection equation. The solution does not grow. The amplification factor is equal to 1, so the scheme is neutrally stable. So let's now discuss another. That was our number one new scheme, although mentioned briefly. Now number two is called the Lax-Friedrichs scheme, and this was introduced in this quite famous paper by Peter Lax. He's still alive. He's an emeritus professor, and he was tremendously important. He laid the foundations for the modern theory of nonlinear hyperbolic equations. There are a lot of methods, numerical schemes that have his name. This is one of them, the Lax-Friedrichs scheme, and we'll see another one later. And he made many groundbreaking contributions to things like solitons and shockwave theory, and so on. It's a tremendous mathematical genius. He emigrated from Budapest at the age of 15 or something like that, and he was early on, as a young man, he was part of the Manhattan Project, where of course he alternated with all the famous, Richard Feynman and all those guys in Los Alamos. And then he went to Courant. I think he went straight to Courant after that. I don't have the straight facts. One of his students, perhaps, you would know, but there's a very famous mathematician in Berkeley called Alexander Chorin. He's also worked on fluid mechanics quite a lot, the mathematical theory of fluid mechanics. He was a student of Peter Lax. And Peter Lax won the Abel Prize. Abel is, like the abelian groups for mathematics, that Abel. And this is a prize which has been introduced kind of similar to the Nobel Prize, but for mathematics, because the Nobel Prize doesn't cover mathematics. And so they get a big prize and almost $1 million, the same as the Nobel Prize, okay, but in mathematics. He won it in 2005. So really quite a fantastic figure in this whole field of CFD and applied mathematics in general. So the key to this scheme is to replace, a clever idea, replace UI by the average. 1/2 UI minus 1 plus UI plus 1. So the average of the 2 points on either side. By doing this replacement, by introducing this, fantastically, this is able to stabilize our center difference scheme for the conventional equation, or center difference in space and forward difference in time. We've been using this center difference in space and forward difference in time, but it is also called the forward time centered scheme, abbreviated FTCS. So in some books you will find it abbreviated by FTCS, and that's what it means. Our unstable one can be stabilized by introducing this little trick of replacing UI by the average. So what we get is UN plus 1 at I is now going to be equal to 1/2 UN I plus 1 plus, it's the average, there's a plus here, UN I minus 1, and we have the same as before for the spatial term, UN I plus 1 minus UN I minus 1. So this substitution here introduces an error, of course. But the error is of order delta x. So convergence and it reduces the scheme. Remember, the centered centered difference was second order. But by introducing this error, we reduced the order of the scheme to first order, but it is now stable. So let's look at how the stencil for this one would look like. So let's consider again our I minus 1 and I plus 1 points in space, and let's consider our point n plus 1 here and n here. And so we're obtaining this value of the solution here with our numerical scheme, and we're using for that only these 2 points. And this one doesn't come into play. So similar to the leapfrogging one, but this is not a 3-level. So u n plus 1 at I does not depend, again, on u and I. But instead it depends on the neighbors of u and I minus 1 and u and I plus 1. So that's our stencil now for this scheme. And this is going to introduce some interesting behavior. But let's look now at the stability characteristics of this scheme by using our trusted von Neumann analysis by inserting the harmonic Vn times Ei phi to the whole equation in the numerical. So we introduce this and get the amplification factor in the usual way after dividing by the common term E I theta, and we get G is equal to, I'm going to skip the derivation of this and you can check it in your own time, minus I, the imaginary number sigma, sine phi. So if we look at this in the complex plane, this represents, basically this represents an ellipse in the complex plane, and I believe I have a figure here. Here it is. So this is our region of instability, where outside of the circle of radius 1, and our ellipse here notice here this value is sigma, and G moves around this ellipse here. So it's an ellipse centered at the origin, but you see that the major axis is 1, the minor axis is sigma, and therefore the CFL condition applies again. Which is simply that sigma has to be less than 1. Let's put less or equal. Basically, we want that ellipse to be inside the stability circle, and that ensures that the scheme is going to be stable. So as before, all we have to do is ensure a relationship between delta x and delta t for stability. Okay. Number 3. Number 3 is called the Lax-Wendroff. And again, here's the paper where this is introduced. 1960. You notice that by doing the little trick that we introduced with the the Lax-Friedrichs scheme, you were able to stabilize a previously unstable method, but introducing an error of order delta x. So again, it's unsatisfactory in the sense that the errors are quite large, can be quite large, and so I was saying the Lax-Friedrichs scheme is first order, which is generally not good enough, and the Lax-Wendroff scheme instead was introduced. It actually was the first scheme that was introduced that was second order in both space and time, with two time levels. Okay, not three like leapfrogging, 2 time levels. And it really is a landmark in the history of CFD. There is, it was the most applied of all numerical schemes for aeronautical applications for years and years, for all through, all the way until perhaps the 1980s. It was the most applied method. Okay, this really was a tremendous breakthrough. For 20 years. So what does it do? The original derivation starts with a Taylor expansion in time. And let's write it. It's a Taylor expansion in time around un. So un plus 1 at I is going to be equal to un at I plus delta t times the first derivative, ut at I, plus delta t halves, delta t squared half, second derivative, utt, that's pretty ugly too, so I'll fix it, utt at I, plus other terms, higher order terms of order delta t cube. So the trick is going to be for this guy to keep the second time derivative in the discretization. And replace the time derivatives by equivalent space derivatives So we're going to use the convection equation, kind of similar to what we did for the modified differential equation. So we're going to use the convection equation. ut partial with respect to time plus c ux equal to 0, and take a time derivative of that, to get, as we've done before, utt equal to minus c ux, again the derivative with respect to time of that, and we can swap again the order of the derivatives to write minus c ut, and now derivative with respect to x, and as we've done before, this is equal to c squared using the convection equation equal to c squared uxx. So now we introduce this in our equation here. I'm going to change color to make it easier to see the difference between all of these writings and scribbles here. And un plus 1 I is equal to uni minus c delta t. We're using the equation to substitute time derivatives with a space derivative. So now I have ux at I. And the second term comes from this one. And here we have c squared delta t squared divided by 2. And we have the second derivative with respect to x at I. And again, our term of higher order, delta t cubed. So you see that here we have an additional dissipative term and what we're going to do next is to discretize the space derivatives with a second order center difference. So now using center difference in space, we get finally un plus 1 I equal to un I. We have minus sigma half, where I'm using again sigma for the CFL number, un I plus 1 minus un I minus 1, our first center difference here, and here we have sigma squared half, and our center difference for the second order derivative, which is un I plus 1 minus 2 uni plus uni minus 1. And here's our Lax-Wendroff scheme. Okay. So a couple comments on this guy. Looking back at the modified differential equation, for the center difference scheme, let's write it in this acronym way, FTCS, forward times centered space. Basically, the Lax-Wendroff scheme is the discretization of a modified convection equation obtained by adding the lowest order truncation error term So this is the equation, basically, that the Lax-Wendroff scheme is using instead of our convection one. And this is the first term of our truncation error. We're adding it back and using and discretizing that term, okay, and keeping it. And so because now we're keeping this term, the Lax-Wendroff scheme has a truncation order which is proportional to the next term, which is uxxx, the third order derivative, okay? The dominating truncation error is proportional to uxxx. And the modified differential equation is ut plus cux plus, so we're keeping this, delta t over 2c squared u bar xx, and on the right hand side we have the terms of the truncation error, delta x squared divided by 6 uxxx, and plus higher order terms of order delta t squared and delta x fourth. This is our modified differential equation for the Lax-Wendroff scheme. Finally, we look at the stability analysis for this scheme, for Neumann stability analysis. And I'm going to obviously skip some steps because you know how to do this already, and just write our amplification factor. You can check it afterwards. It leads to 1 minus sigma half times e I phi minus e minus I phi, e to the minus I phi, plus sigma squared half, you can see where all this is coming from, e I phi minus 2 plus e to the minus I phi. This is equal to 1 minus I sigma sine phi minus sigma squared 1 minus cosine phi. Here we have again to take the real and imaginary parts to see how this looks in the complex G plane. And so the real and imaginary parts real, that's usually psi is real of G is equal to 1 minus sigma squared plus sigma squared cosine phi, and eta, the imaginary part of G, is equal to minus sigma sine phi. So in the complex G plane, again we have an ellipse. This is going to be an ellipse centered on the real axis at the point 1 minus sigma squared with semi-axis of sigma squared along the real and sigma along the imaginary. Directions. Okay, so this ellipse, and I have a picture, but before I bring on the picture, I think I didn't leave enough space, so I'll let you take notes of that so I can clear the slide if necessary, clear my annotations. And we have the ellipse centered at this point 1 minus sigma squared on the real axis, and there are two situations. You could have sigma squared greater than 1/2, and if sigma squared is greater than 1/2, this point is closer to the origin than to 1, and if it's sigma squared less than 1/2, then this point is closer to 1, you see. And so in either case you have an ellipse which is vertically positioned like that, but it's always contained within the unit circle if sigma is less than 1, again leading to the CFL condition of so this ellipse always contained in the unit circle, the circle of stability, as long as, again, sigma less than 1 or our CFL condition. So we have, as for most of our previous schemes, the same condition for stability. Okay, so what I want you to do is take the code that you have for step 1, okay? But let me clear these annotations. Try a step function. So the function, the initial condition, suppose it's going to be just 1 at the value x equals 0. Your first point is equal to 1, and then all the other points are equal to 0. But as the solution advances, you're feeding points equal to 1 on the left, okay? Okay, so what I would want to use as an initial condition is simply a step function that's traveling in that direction, okay? So start with simply at x equals 0, just a 1 point basically that has equal to 1. Every other point is equal to 0, okay? And this is going to move here with c equal to 1. So basically at time equals 0, it's going to be like that. And at time greater than 0, you're supposed to have this, again, moving that direction. Okay, that's your initial condition. Basically, you make your border here, your boundary condition be equal to 1, so u at 0 equal to 1. This is going to be your boundary condition, and your initial condition basically is a Heaviside function. Okay, and so try first your first order upwind scheme, which is the one we used for step 1. Then try, well, whatever order you want to try them, but you're going to try the ones that we have, Leapfrog, the ones that we have shown today, Lax-Friedrichs, and Lax-Wendroff. Look at that, what happens. And next class, we'll have a little bit of a discussion about the features of these different schemes, and we'll go on to discuss some aspects of numerical dispersion errors now.